On this episode of Beyond the Forecast, we're going to be talking about this, the Nancy Grace Roman Space Telescope. In the first 5 years, it's going to cover 50 times more of the sky and the night sky than Hubble has been able to do for the past 3 decades. It'll be able to gather that information faster too, about 1,000 times faster with all that new tech that's on board. I'm really getting excited to see what's going to be with this telescope. Now, how much data is that? Around 20 petabytes or 20,000 terabytes. That's a lot of data. It's a lot of space. That's over the first 5 years of that primary mission. Now, not only is it going to study a huge part of the sky, it's also going to be looking for exoplanets as well. So basically planets that are orbiting stars using a coronagraph. We're going to learn more about that in this video and in this episode, so stay tuned for that. And then, in addition to that, this will be going into a position near L2, close to where the James Webb Space Telescope is. So where is that? Well, we're going to talk about that as well. So we're going to learn more about the universe in the months ahead from Roman Space Telescope. Recently, NASA gave us a little bit of an insight and an update on where is the telescope now, what's going to be happening before launch, and what's going to be happening shortly after launch. So to get started, here's Sean DeMoggle-Goldman, the director of the Astrophysics Division at NASA.
Dr. Roman was a brilliant astronomer, and she realized how much power we would have if we could get telescopes up above Earth's atmosphere, which otherwise gets in the way of our observations from the ground, and how it could complement the astronomy we can do from the ground. She had the technical acumen to detail those arguments and the leadership and political capability to explain that to her peers and to stakeholders. And although she's often most associated with those first space telescopes, it's really our full fleet that she deserves credit for. And every time we build a new space telescope, we add to that fleet with capabilities we didn't have before and that add to her legacy. And that telescope, that's her namesake, the Nancy Grace Roman Space Telescope, is no exception. The best way I could describe how it's going to add to our fleet is by going through an extended analogy of someone taking photos of a forest. By getting telescopes up into space, we can have the sharpness that let us not just take pictures of the forest itself or the trees, but in some cases the leaves or the birds in those trees. That's what we did with Hubble. With the James Webb Space Telescope, we could take pictures of those birds and leaves and further off trees. And with our survey telescopes like SphereX, which we launched last year, we can take panoramic views of the forest itself. Roman does both. It has that wide-angle view of the forest and the sharpness to see the birds and leaves on those trees. Of course, this isn't a forest we're talking about, it's the known universe. And those birds and trees are supernova and galaxies and planets and stars. In many ways, the astronomical target that Roman is chasing and designed to study is the universe itself.
The launch coming up for the Roman Space Telescope will be on top of a SpaceX Heavy rocket, Falcon Heavy rocket, the one with the 3 big columns that'll help get this thing not just into Earth's orbit, but beyond there. It's got to get to L2. Let's talk more about what happens right after launch from Jeremy Perkins, the Roman Telescope Integration and Test Scientist at NASA.
Right after launch, lots of us are going to be sitting down in Florida and up here in Maryland and out in California, monitoring our systems and making sure that Roman is operating like we know it can. It's taken a lot to get here. A lot of planning, building, testing, and practicing, sometimes in windowless rooms and sometimes in clean rooms and labs and in universities and at scientific meetings around the country and around the world. So SpaceX should put us in a really good orientation after we separate with our solar panels pointed at the sun and our instruments safely on the other side of the observatory. But right after separation, we're going to be activating Roman, and it's going to be actively making sure that our solar panels are going the right way. We deploy the side panels and the sun shield, and we start checking out the propulsion system. Right around the end of the first day, we use that propulsion system to make sure that we get sent in the right direction towards Lagrange point 2, about 1 million miles from Earth.
So you probably have heard about the Hubble Space Telescope. Here's a 3D printed model that I made for you here to kind of give you an idea of what this telescope is able to do and what it looks like. Obviously, an incredibly cool looking machine. This telescope orbits the Earth. That's the key thing. It orbits the Earth about 300 miles up. Because of that position, there are some limitations when you're orbiting the Earth versus if you're in another position in space. But the Hubble, launched in 1990, this is part of the shuttle program. During several shuttle missions, they were able to go up, astronauts were able to go up, grab it, adjust some things, upgrade some parts, so we still have it in service today. Eventually it'll be decommissioned, but it's been an incredible machine since it's been launched and especially since it's been updated. Now this is really cool. This is another model that I was able to bring in for you here. This is the James Webb Space Telescope. Now the difference that you see here compared to the Hubble is that the primary mirror is this big yellow area that's exposed right here. This is not in orbit around the Earth. This is in a totally different position outside of Earth's orbit, but still kind of sort of connected. This is sitting in a position called L2. So come on over here, let's get over closer to the monitor and let me show you what's going on. So we have Earth right here, we orbit the Sun as we all know. L1 is a position that is in between the Earth and the Sun. So a lot of our solar observing satellites that look for solar storms, sunspots, the Solar Dynamic Observatory, when I show you those videos and those images, those spacecraft are hanging out here. They also can sit as an early detection system if there's ever a really strong solar storm that can come our direction, because they're a little bit ahead of the Earth, about 1 million miles away. But there's an opposite side, L2. That's behind the Earth. Now, it's not an Earth's shadow. Don't think of it like that. It's still a very large area. Spacecraft like the James Webb Space Telescope sit there. They can safely sit there for about 23 days before their orbit and their position needs to get readjusted with some thrusters. But this is a great spot for satellites to sit. You can get farther away from the Earth so you don't have to worry about the orbit and getting into the light and then being in the dark area. You can face away from the Sun and always get a clear view of the cosmos, obviously away from the Sun. So as the whole system goes around the Sun throughout different times of the year, we can look at different parts of the cosmos and of the sky. There are some other Lagrange points that are on the map here too. So we have L1, we have L2, there's also L4 and L5 that can be used. And one that really wouldn't make any sense, but it would be kind of cool to have a spacecraft at L3. The problem is that you'd have no way to communicate to it because L3 is always opposite of the Earth and you can't shoot signals through the Sun. It just gets in the way, it causes interference. But that's where not only the James Webb Space Telescope is sitting, that is also where the Nancy Grace Roman Space Telescope will be sitting after launch. It'll take a little while to get there, but that's where it's headed. Now the fun part, we're going to learn the differences between the Hubble Space Telescope, the James Webb Telescope, and the new one, the Roman Space Telescope that's soon to be launching. Julie McHenry, the Roman Telescope Senior Project Scientist at NASA Goddard, has more.
Okay, so Roman has broadly the same sensitivity and sharpness of vision as Hubble, but we survey the sky much faster. So that 1 month of observations to survey our Milky Way galaxy would take about a century with Hubble. So that's the edge that Roman has over Hubble is our ability to sweep out large regions of the sky. That opens completely new science questions for us to address. Our comparison with Webb is a little bit different. So Webb is designed to be able to probe very deeply and with exquisite sensitivity into the universe. So it can find rare things in the early universe. But you need Roman to find rare things in the more nearby universe. So for example, one of the discoveries with Webb is little red dots, these small point source objects. But Webb isn't able to find enough of them nearby to figure out how those red dots evolve. And that is something that Roman can address. So basically, we provide the large vision that complements the deep views that Webb provides. Roman was motivated in part by the discovery in the late 90s that our universe isn't expanding at a steady rate. It's not decelerating like you might expect from gravity acting on the matter in the universe, but it is actually accelerating. And that's an incredibly exciting thing to study. But in the time between then and now, it's become even more exciting because we have a straightforward, in a cosmological sense, a way to explain how the universe works that really, really well connects what we see in the early universe with the cosmic microwave background to what we see now today. So we map the expansion rate, what structure should look like. And that had been fantastic, but there have been hints in the last 5 to 10 years that all is not well with our standard model. There are hints that the Hubble constant, which describes the expansion of the universe, is not quite consistent or not as predicted by this model. There are hints that the distribution of matter, the structure of matter in the universe, is not quite right. And there are even hints that the cosmological constant, a constant property of space-time, is in fact not constant. And all of these mean that Roman's observations are so much more exciting now, because we're probably not going to confirm a standard model of how the universe works. We're very likely to demonstrate that our standard model is wrong and to set ourselves on a path to figuring out how does our universe really work.
There are two main instruments on board the Nancy Grace Roman Space Telescope. You have the wide field that you can get those huge images of the cosmos that we started with, about 50 times more of the sky than Hubble. That's going to be awesome. But also there's the coronagraph, and that's where we can see the small planets that are orbiting distant stars. To learn more about that, let's have our conversation. Let's go back to that conversation I had with Jessica Bailey, the Roman coronagraph instrument scientist at NASA JPL. She's going to give us everything we need to know about the coronagraph. So first of all, you must be really excited and really proud because something that you've been working on for a long time is going on that telescope inside of that room. So how do you feel right now?
Oh gosh, yeah, this has been a long time coming, and I'm thrilled. So I'm on the science team for the coronagraph instrument, and I've been at JPL since 2017, which puts me kind of midway through the project. There are folks who've been working on this all the way since its inception, decades. I'm standing on the shoulder of giants to get to this point, and I'm so excited for the first photons that are going to come in, and within a year we'll be doing science.
Yes, and the coronagraph, give me an overview to a fifth grader how a coronagraph works, and then we're going to talk about the spacecraft specifically. So just give me that overview.
Yeah, well, if you want to see a bird or a plane next to the sun, you put your hand up, block the sunlight. It's the same thing. We're blocking the light of a star to see a planet next to it that's much fainter.
And then, so how are we going to use that on this spacecraft and for this mission?
Yeah, we have very specialized optics, mirrors, and masks within the coronagraph instrument that will block the light of other stars to see planets around them that are maybe 10 million or 100 million times fainter, to see something like Jupiter around our own sun.
So we're looking at distant, large planets surrounding and orbiting, rather, these distant stars. Since the field of view is so wide, are we going to be able to maybe take a look at a bunch of different spots? Is that the idea of this?
Right.
Or are we looking at two different instruments and am I getting confused?
Exactly. So there are two different instruments on the Roman Observatory. There's the wide field instrument that, will be able to survey the sky 100 times faster than Hubble. Then there's the coronagraph instrument that takes the narrowest of soda straws and looks at individual systems to look for those planets with the direct imaging in great detail. The wide field instrument uses totally different techniques to find exoplanets. Uses something called microlensing, something called the transit method. It will take census of planets around other stars, and then Roman coronagraph will study a few Jupiter-like planets in great detail. They won't be the same planets, but they're going to give us very complementary information about the census of planets and what their properties are. So the coronagraph technology that we use on Roman coronagraph is kind of the next generation compared to what's on the James Webb Space Telescope or the Hubble Space Telescope or even ground-based telescopes. We're building on all of that heritage. Mm-hmm. What astronomers can do today with coronagraph instruments are see planets that are maybe 1 million times fainter than their stars, and primarily in the infrared, where those hot young Jupiters are still glowing from the heat of their formation. What we're doing with Roman coronagraph is hopefully getting to 10 million to 100 million times fainter, maybe even a little bit more if in the best case scenario. that might allow us to see light reflected off of the cloud tops of a cold, old Jupiter analog invisible light for the first time. The technological improvement that allows us to do that is not only more specially designing the starlight blocking masks and optics, but also using something called deformable mirrors. Exactly what it sounds like. They are mirrors that have thousands of tiny pistons on the back that can move at nanometer or even picometer scales to correct the very small polishing errors or optical misalignment errors in the system to block out light better, as compared to something like Webb or Hubble that doesn't have those active deformable mirrors. This will be the first time we're using those in space.
How do we know when we're using those deformable mirrors what it needs to be? Is that the system saying, oh, if I want to have this ideal image, I need to deform this way to position A1A versus A3B? Is that how it works?
Yeah.
Kinda?
Yeah.
Okay.
We're using our science camera images themselves. We build a model of how a poke on one actuator on one deformable mirror translates to a little bit more starlight glare in a particular pattern in our science camera image. So then when we see that pattern, we can poke that actuator. Of course, the optimization of that mapping is, the devil's in those details. But yeah, we're using our science camera images to create the commands for our deformable mirror, and we iterate back and forth until we've suppressed as much starlight as possible from our science image and hopefully seeing the little planet.
Fascinating. This thing's going to be launching maybe later this year, and that first image from the coronagraph, what's kind of the timeline for that after we get it into position L2?
We have, after we launch Roman, we have about a 90-day commissioning phase. That means for both the coronagraph instrument and for the wide field instrument, we're tuning them up. We're making sure that all of our capabilities work. We're getting an initial calibration. That takes 90 days. Then we'll transition to regular ops, and at that point we'll start getting to use it for science and for pushing our performance a little bit deeper. Yeah, I mean, I guess this gets back to your former question about how many things we're going to observe. Right, so we're not the coronagraph instrument is not a survey mission. We are going to stare deep for a long time at a much smaller number of things. Think of 10 or tens of systems, not thousands or millions of systems like the wide field instrument will survey. There are some nearby systems, maybe like the Epsilon Eridani system, or perhaps the Epsilon Andromeda system, as well as just some of our very nearest solar neighbors that I'm very interested to see. Are they're known to have planets that haven't been imaged before, or some of these systems, like Sean Domingo-Goldman was talking about for the Habitable Worlds Observatory. They may want to look for Earth-like planets around these stars in the future. One of the potential confounding factors there, though, is what if the systems have too much leftover dust from formation? It's too dusty to see those Earth-like planets. This is something that I think Roman coronagraph will be able to help with, because we'll be able to get the deepest images ever in visible light in some of those nearest by systems that might be interesting to look for Earth 2.0 in the future to see, are they clean enough for those Earth finders down the road.
And is that because of the deformable mirror, or why is that?
Yep, the deformable mirror combined with the optimized coronagraph masks combined with the exquisitely sensitive or exquisitely stable telescope. That's something that I guess I haven't mentioned is the Roman Observatory is just wonderfully stable, and it's out in this L2 orbit. It's not going in and out of the sun like Hubble does, so it will be stable, more stable than all of these other observatories that we've built before, and that's what allows us to do starlight suppression at these unprecedented levels.
Did they tap in a little bit of that knowledge from James Webb Space Telescope for the stability for Roman?
I mean, I'm sure that's the case. That gets a little bit outside of my expertise,
That's
knowing
fine.
how much crosstalk there was between those two. But yeah, certainly, there's a lot of heritage there in understanding what kinds of materials are the most stable in space and how do they perform. Like the modeling has been a very important aspect of designing the Roman Observatory, has been developing some of the most precise models of how it will perform under certain circumstances, so then we can design our observations to be constrained within their recommendations for how we can make the observatory even more stable by designing observations intelligently.
And then I have one final question, just kind of your takeaway. We're all excited for this to launch, we're all excited to see, but you've been working on this for so long, so just some final thoughts on that.
Oh gosh, I mean, I think it hasn't hit me yet, if I'm being honest. But that, at this point, we're planning towards launch in early September. And I'm really excited to be in Florida in September to see the observatory launch and to be, collecting these photons that have been traveling towards Earth for years, and to capture them in my detector and get to build a better picture of our nearby solar neighborhood.
As my meteorologist day job, I will try my hardest to make sure during peak of hurricane season there are no storms near Florida.
Thank you.
Launch time, high pressure.
Thank you.
So thank you very much for your time.
Yeah,
nice to
very
meet you
nice to
too.
meet you.
Yeah. One last question that I have for the team. How many people are going to be involved with the Nancy Grace Roman Space Telescope after it's launched, after it's operational? And what can we learn and what does it mean for us here on Earth that are interested in looking at what it can see?
And if you think of the wider group of people that are actually working on Roman, it's going to be hundreds to thousands, because the data sets that we produce are open to the whole country and the world. And the folks that are going to be looking at Roman's data and doing science with Roman is almost uncountable in terms of the reach that we're going to have.
Do you want to name some of the primary locations?
Yeah, so we've got teams up in Maryland, both at Goddard and then up in Baltimore, and then out in California at IPAC and JPL, as well as universities around the country that are also working on Roman's data.
Because our data are immediately available to everybody in the country at the same time, that you can be a teacher in a high school in Kentucky and your students have the opportunity to see Roman data, new Roman discoveries at the same time as a professor in Princeton. And I think that there's a place for helping people get really excited about the amazing things that we're able to build.
Yeah, and for me, I think this, this comes down to two things. One, the first thing I said is, in NASA astrophysics, we pursue the big questions. Are we alone? How do we get here? How does the universe work? And Roman's going to help us answer those really curiosity-driven questions. Like we're nerds, like we're NASA, like we love that stuff. That's why we do this. But when we do these things, especially for the flagships, we're setting out to do stuff that's like not possible. Like the stuff we're gonna do with Roman isn't possible today. It won't even be possible when we launch it. It won't be possible until we're done with the commissioning and it's like well-tuned, right? When we set out to do the impossible and then achieve it, it's not just our impossibles that become possible. Like to give an example, when we built Hubble and Webb, we were chasing far-off galaxies in the farthest corners of the universe. But because we have a Hubble and a Webb, we're able to track asteroids that would pose a threat to Earth or to future lunar outposts on the lunar surface, right? Those were impossibilities that are now just possible and sometimes routine. There's things that go into medical imaging devices in our cell phones that come out of stuff that was impossible until NASA did it. And now it's so routine you carry it around in your pocket. So, we're nerds. We chase the curiosity-driven impossible stuff, but we make a lot of other stuff routine that impacts our daily lives in many, many ways.